Alt R. Yes, there we go. Now we are recording. So let me go ahead and close my chat window, open up the Q&A window. One question that someone has asked here, right? Can you more or less attend whatever lecture that you would like? And yeah, so if you would, if you're formally in another class and you would like to also view my class, right? We don't keep attendance or award attendance credit kind of in any of these. And so especially when it's online, we certainly have the space. Of course, if it's an in-person and we're running out of chairs sort of deal, I may have to revise this policy, but for the time being, yeah. And then I have how have you been doing? I've been doing all right, except for, I was looking forward to, being live in person here, and now we're back online. So I'm a little bit bummed with that, but aside from that, I'm good. So, all right, a little bit about formatting, and then we're going to be learning some math today. So I posted this announcement. Hopefully you guys saw it. So this is, for my sections, if you're not, in one of these sections 7 through 12 that I'm formally teaching, you still have access to all of the same information. It's just you don't get this announcement right here. So I'm going to be using a system, right, where you have some class notes, some kind of fill in the blank style PDFs that you're going to be downloading. I have some class videos that I'd like you to watch before coming to class to give you some basic definitions, theorems, stuff like that. And then while we're in class, we're going to be primarily engaged with how do we actually use these things? How do we use these definitions? How do we use these theorems in order to solve problems? So let me show you where this stuff lives, just so that everyone can access it. And our main navigation bar here under the quick links, we have space for each one of the instructors to post things. And these are open folders, right? Really, any student in any of the sections can view any of the content posted by any of the instructors. So, I mean, it's kind of like one of those things that might as well have more learning opportunities. And so if you go to my lecture 2 stuff here, I have a little bit of, an order of operations that I've written here, how to learn in this class. And then I have posted here, right, our exam 1 content covers primarily chapters 12 and 13. So I have some notes, and then I have those pre-class videos that I would like you to watch ideally before coming to class. Another question that came up, will you record these lectures when we go back online? I think you mean back in person. If it's reasonably done, then yeah, I would be happy to continue to record these lectures when we're back in person. However, if it's difficult to do, like if I have to hire someone to, bring a record, some sort of setup, then not so much. Are we required to attend recitations? No, you're not required to attend recitations. There is a weekly review document that is done in recitations. And so I would say if you're having problems with that weekly review document, go ahead and, you should come to recitation, and that's worth some credit. So you do have to scan that and upload it, and you get some credit for that. More details are in the syllabus. Okay. With that, I think I have the main highlights covered. Of course, right, you should also read through the syllabus in great detail. Thursday's recitation will be covering a little bit about that. So that'll be Thursday's recitation. And then also, if you're wondering, what are we going to be covering, or, when you're looking at the notes and whatnot, and just kind of seeing the order here, that's all covered in the schedule. So these right here, I can zoom out a little bit, close that. So you can see today we're talking about 12.1 and 12.2. Wednesday we'll be talking about 12.3. All of these numbers right here are referencing our specific course textbook, which is Stewart 7th edition. It's the same textbook that we used also for Calculus 1 and Calculus 2. In fact, I have a copy of it, a full copy of it right here. There it is. Big old, 1,500 page or so textbook, but it's the same one that we use for Calc 1 and for Calc 2. And it's an old edition, right? I think they're on like 9th or 10th edition sort of deal now. You can get these used on Amazon for $40 last time I checked, sometimes less, depending on if they have more or less of those. So anyway, a few options for the textbook there. I recommend it just for kind of extra exercises. Okay, well, with that, let me pause and just kind of double check the Q&A. Looks kind of blank right now. Next up is that we're going to start learning some math today. So I'll just pause for maybe one more second, see if there are any other administrative question things, and then we'll go into learning the 12.1 and 12.2 for today. Okay. Good enough. Then I'm going to go ahead and stop sharing on my desktop and start sharing on my iPad. And maybe the first thing, well, it's taking a minute for it to wake up here. There we are. So before today's class, I'm not sure if you happened to see that announcement before class, but I did have a pre-class video. And so I'd kind of like to quickly go over some of the highlights, some of the main things that we are meant to take away from that pre-class video, and then we'll kind of continue into the day's lesson. So if you didn't have a chance to watch this one, that's fine. I understand it's the first day of classes by all means. But hopefully for, future classes and whatnot, you'll have a chance to take a look at these before coming to class. Okay, so we talked about upgrading our two-dimensional system into a three-dimensional system. So we have, instead of just X's and Y's, we have X, Y's, and Z's. You can see the convention for this is to take this XY plane and set it flat on your desk. And then that third dimension, this is new Z dimension, comes kind of out of your desk, right? So here you can see the X, Y, Z. And let's see, I have a Q&A. Question about structure for this class. Yeah, it's similar to the Math 133 structure, right? So you'll continue to have web work, homework. We'll have quizzes and exams and D2L, all that sort of stuff. And we have these pre-class videos. So yes, it is quite similar to the 133 structure. So we have these formal definitions here, right? We have still coordinate axes, but now instead of just the x-axis and the y-axis, we now have a z-axis. The common meeting point is still the origin. This z-axis is not random, kind of the way that it comes out of the x, y plane. You have to follow this thing, the right-hand rule. And this becomes very important later on when we're talking about in like 12.4 or so, we're going to bring up this thing called the cross product, right? The cross product is this interesting way to multiply two vectors together. And it also follows this right-hand rule. So again, I would make sure that you go back and rewatch this, the video, the actual, pre-class video here, if you're confused about this right-hand rule. Instead of quadrants, you have octants, right? And there's not really a convention for all of the octants, but everyone agrees that the first octant is the one that has all the positive axes, just like the first quadrant. So, right, we have a first, second, third, and fourth quadrant. Octants, no one can really agree on how these things should be enumerated. There's not any like conventional way to do this, but at least folks can agree that the first octant will be the one with all the positive axes. So that's kind of uniform across any math textbook that you see. We did a little bit with plotting, a little bit more with plotting, and then we did some notation stuff, right? So when you see something, the script R with a little 3 above it, that means that you're in three-dimensional space and your components are all real numbers. So this R quite literally is standing for real numbers. So you have a real number, a real number, a real number. So you have an X, Y, Z such that each one of these components, the X component, the Y component, and the Z component, are all in the real numbers. So this right here is called set notation. This straight up and down right vertical bar here usually stands for such that. The first part of set notation tells you what the elements in the set look like. And then the second part tells you any restrictions. So again, this first part is telling you kind of, these look like ordered triples, right? Inside of parentheses, all that sort of good stuff. And then after that, the conditions are that X, Y, and Z, these components are all in the real numbers. This right here means in the real numbers. So that's kind of the standard three-dimensional rectangular coordinate system. Yeah, so I will post the live lectures after class, after they've had a chance to actually compile and all that good stuff, I'll go ahead and post them in that folder that I have. So yes, they will be posted. All right, good. Well, that is the pre-class videos on 12.1. We're going to focus in class today on the rest of 12.1. And actually 12.2 is introducing vectors. I think that many folks have probably seen vectors. And so you may notice, let's see, I think I actually, do I still have that page? No, I do not still have that page. But so the vector stuff, the 12.2, I just have a couple of videos for you to watch about that. But we're going to be, of course, upgrading, talking a lot about vectors, in 12.3, 12.4, kind of, a lot throughout the rest of the semester. And so today we're going to kind of focus on the 12.1. I think that's maybe the more interesting stuff, the stuff that we could really use a refresher on. And the 12.2 stuff, again, I have those videos for you to take a look at. So make sure you do that before Wednesday's class. Okay, so we are upgrading. In the pre-class stuff, we talked about points in space, right? And now I'd like to talk a little bit about surfaces in space, right? And kind of just as a refresher here, before we kind of get into drawing surfaces in space and whatnot, I have a quick exercise just to kind of remind us, because a lot of this chapter 12, right, you'll notice that we're not actually doing integrals. We're not actually doing derivatives, right? We're doing algebra. This is kind of the algebra. We're doing a very quick chapter here. What took, previously entire semesters, of you learning algebra and whatnot. We're going to do kind of a quick chapter here on how to upgrade a lot of this stuff into 3 dimensions. And so, again, notice you won't have any derivatives or any integrals throughout chapter 12, really. So I'd like to just kind of remind us, determine if the point 1,4 is on this line. So we have this line. And again, I'm thinking about back in my old algebra days. If I wanted to determine if this point was actually on this line, what do I do? So if you wouldn't mind either typing it in the Q&A or typing in chat, I'll take a look at chat if you want to type there. What do you do in order to determine if that point is actually on the line? Yeah, so I see it here, both in the chat and in the Q&A. I appreciate it. Yes, that you plug it in, that you go ahead and you substitute in everywhere you see, right? We know that this first coordinate right here is supposed to be the X coordinate, and we know the second coordinate right here is supposed to be the Y coordinate. And so we can literally substitute those in, right? Everywhere I see an X, I'm going to plug in a 1. Everywhere I see a Y, I'm going to plug in a 4. And of course, right, the order there matters. And we see, does this satisfy the equation? Does this actually equal 1? And so in this case, right, we get negative 15 is equal to 1. That's nonsense. So the answer is no, that this point is not on this line because it doesn't satisfy the equation. So there's a little bit of kind of, right, we're making this subtle jump between geometry, right, is a point on a line versus, right, a very, very algebraic thing that we're doing in order to check this geometric statement, right? Does this point actually lie on this line or is it off the line? And same sort of deal happens here when we upgrade, right? So it turns out that this right here is an equation for a plane. So in X, Y, Z space, right? In space, R3, right? Now we have 1, 4, 2, and the way that we're going to check this is the exact same. And we remember that, again, this first component will be the X's, the second component will be the Y's, and the third component will be the Z's. But again, the strategy is the exact same. We plug this in, so we get 1 minus 4 times 4 plus, 8 times 2. And so let's see, I still get my negative 15, but now I have this plus 8 times 2, which is 16. So negative 15 plus 16, this indeed does equal 1. So in this case, the answer is yes. So if we were to sketch this, right, we had some plane floating in space sort of deal. A plane is just kind of this infinite sheet of paper. It's kind of the upgrade, for the XY plane, but it may not sit exactly flat. It may be tilted or something like that. In this case, we would have the point 1, 4, 2 would be a point on this plane rather than some point, kind of off hovering above it or below it or something like this. It's actually on the plane. Okay. Moreover, we don't have to have such just, nice, simple equations. You can have relatively complicated equations. And the game really is not that much more difficult, right? So again, we have X, Y's, and Z's. We can just plug these things in. So in here, we're going to have 1 times -3 times 0 plus 1 squared. Does that equal to Y, which is -3? So 0 times anything is going to be 0. 1 squared is going to be 1. And I can now see that the answer is going to be no. So although I don't know necessarily what this surface looks like, this seems like a very complicated thing, right? Although I don't know what the surface looks like, I can tell you whether or not points exist on it, right? And in this case, the point 1, -3, 0 isn't on this particular surface, whatever it might look like. Okay, now we'd like to switch gears a little bit. And like I alluded to at the beginning of this, during class content here, right, that we're going to try to sketch and kind of be interested in entire surfaces. So now we're switching gears, and I would like to graph, well, my end game goal here, I guess, is to be able to graph a relatively simple equation, y equals 1 in space in R3, right, with X's, Y's, and Z's. And I think in order to do this, right, again, we're kind of upgrading from a two-dimensional world into a three-dimensional world, right? I think it does actually help us to make these connections. And so why don't we first go ahead and graph y equals 1 on the XY plane. We'll describe it as best as possible. And I'm going to kind of introduce this, kind of in a very, well, it's one way to think about this, right? So back when you first maybe graphed y equals 1 for the very first time, back maybe a long time ago in your first algebra class or so, you would probably make a table, right? You would have X's and Y's, that sort of stuff, and you'd plug in different X values into your equation, and you would see what Y would become. And this, again, is a very simple one, so it's rather boring, right? So you might have chosen things like X equals 0 and 1 and 2. You may have even chosen like negatives, like -1 and -2. And in this case, right, every single time when you plug in any of these points, Y doesn't care at all about X, right? Y is just always 1, 1, 1, 1. So if you plug in 0 everywhere you see an X, Y doesn't care, right? So again, this is kind of a very, it's kind of tricky because it's so simple, because it's, right, there's nowhere to actually plug in an X. So no matter what you plug in, right, you always get out 1. And so if you plug in, right, here's my X and here's my Y, X equals 0, we get out the Y value of 1. X equals 1, you get the Y value of 1. X equals 2, you get the Y value of 1, right? And when you connect all of these possible, right, inputs, right, we could do X equals 3 and X equals 2.5 and all this sort of stuff, right? We now are very fast, and we know and love this as a nice horizontal line, right? So if I'm trying to describe it in words as best as possible, I'm going to say that it is a horizontal line. We could even go in and kind of specify, right, anytime we have lines, we know that there's really two main parameters that we're interested in, right? The slope and the intercept, or the y-intercept. So, right, horizontal kind of takes care of the fact that, right, the slope is equal to 0. And, right, the y-intercept, right, thinking about this as a y equals mx plus b sort of business, right, we know that the y-intercept is 1. Okay. Now let's upgrade this. Instead of just the XY plane, I'm going to try to graph this in R3. So let me go ahead and I'm going to draw out my coordinate axes. Usually something like this. The X is over here, Y is over here. This is kind of the standard view for our X, Y, Z. And you can see if you were to hold up your right hand into this and have your fingers curl through the X axis, the positive X axis first, and then the positive Y axis second, right? Your thumb would be pointing in the direction of the positive Z axis. So it's pointing up here. If you were to switch these around, by the way, and have X over here and Y over here, then actually the positive Z axis would be pointing down. So again, this is all that right hand rule, which right now it's but later on in 12.4, it becomes much more important. And so not a bad thing to start thinking about the right hand rule now. Okay, so in this case, we now have X's and Y's and Z's, right? And we can see that the equation here is still just y equals 1. So you can think about this as if you plug in any old x and any old z, right? Our equation really doesn't care about these in any way. Notice I wrote it kind of in an interesting order here, but we know that no matter what you plug in, y is always going to be 1. One way of thinking of this is that equations are equivalent to restrictions. So when we have up here y equals 1, notice that we do not have any restriction on x. X can be anything it wants to be. X can move left and right, right? It can be a small value, it can be a large value, anything like this. There are no restrictions on x. However, there is a restriction on y, right? Y has to be equal to 1. You can't go up, you can't go down, right? It's always just a solid 1. So same sort of thing over here, right? There are no restrictions on x. There are no restrictions on z. X and z can be anything that they would like to be. They can be small values, large values, anything like this. But the only condition that we have is that y has to be equal to 1. So again, you could kind of plug in things like 0 for both of them. You could do 1 and 0. You could do 0 and 1. You could do 1 and 1. You could start doing 2s here and there, right? And we could plot a few of these. So let's go ahead and plot a few of them. So 0, 0, 1. So I'm not moving at all in my x direction, not moving at all there. I'm moving 1 in my y direction, so maybe out here. And then I'm not moving any up and down. So that's the point 0, 1, 0. If I was to kind of reorder this back to how it should be, right? With the x's first, the y's second, and the z's third. Okay, next point here. We have 1 in the x direction. We have 1 in the y direction. So let's come out here, 1, and we're not moving any in the z direction. We're not moving up and down any. There's that one. And notice that, right, we could kind of continue in this direction, right? We could do x equals 2. We could move out this farther. And again, y would have to be still 1. Y would still have to be 1 back here as well. So long as y is equal to 1, right, x can be anything that it wants to be. And likewise, z can be anything that it wants to be, right? Maybe I don't move at all in the x direction. I move up 1 in the z direction, but again, y has to be equal to 1. So again, in my y direction, I have to move out 1. But also z could be equal to 2, right? So long as y is equal to 1. We could also have, right, x and z both being 1. Right? So if I go 1 out in my x, 1 up in my z, so long as y is equal to 1, that's perfectly fine. And so let me pull up chat here and ask you guys this question, right? What kind of, right, thinking about what words am I going to use to describe this surface? Does anyone know what kind of surface this thing is? So yes, this is overwhelmingly, I see the right answers. Thank you very much. It is indeed a plane. So you can see kind of this entire line this way is perfectly fine, up and down, perfectly fine, even moving, you know, off to the side like we had there, 1, 1, 1. So long as you're in this y equals 1 sort of space here, then you're fine. We are on the surface. And so this is indeed a plane. So x and z can be anything that they'd like to be. You notice that you can travel freely in this x direction and freely in this z direction. But the only direction that's kind of fixed, the only direction that actually has a restriction is the y direction, right? Y has to be equal to 1, but otherwise you have kind of a copy of this xz plane sort of deal, just kind of been pushed out a little bit. It's been pushed out and we have, you know, y equals 1 rather than maybe y equals 0 would be the traditional xz plane. The other thing that I did want to bring up to you guys, I noticed, I mentioned at the beginning of class, right, that more or less, I was going to leave the chat for you guys to kind of talk there. I was going to primarily look at the Q&A. I do also accept, right, if you want to raise your hand at any point during the class and you want to, just verbally ask your question, that's also certainly fine. So I will also get like a little notification if anyone has a raised hand, and I'm happy to call on you, especially if you don't want to type it all out. So just as a heads up, kind of for any time that you want to ask a question. Okay, so let's go ahead and move on here. Same sort of game, more complicated. Instead of just a classic, y equals 1 sort of deal, now I have x squared plus y squared equals 4. Let's first do this in the xy plane, describe it in words as best as possible. Then we're going to upgrade and see what this looks like in R3. So x squared plus y squared equals 4. I'm hoping, right, that many of you are very fast at this, right? You can just look at it and you know what this sort of thing is immediately. And that shows you, right, that not every single equation out there we need to necessarily get into a y equals format, right? So this one, x squared plus y squared equals 4, this should remind you of the classic x squared plus y squared equals r squared, which is a circle centered at the origin with a particular radius. So I can draw this awfully fast just because I know that this is the standard setup for a circle, and the radius is 2, right? Because 2 squared equals the 4, which is on the other side of the equation there. Moreover, I know that it's centered at the origin because these x's and y's haven't been shifted at all. So I can sketch it pretty fast and I can describe it, right? Again, this is a circle. And with circles, you need to usually say, right, the two parameters that you're maybe interested in is where is the center and what is the radius. So the center is 0, 0. And the radius is going to be 2. Oops. There we go. So if we play the same sort of game down here, right, I would like to graph now this in R3, x squared plus y squared equals 4, describe it in words as best as possible. So again, let me go ahead and draw out my coordinate axes, x, y, z. And notice that, again, thinking about this as a restriction, right? X's and Y's have restrictions on them. They can only really lie on the circle sort of deal, right? For instance, you could never have an X value of 3, right? If you have an X value of 3, then you'd have something like 3 squared plus y squared is equal to 4. This would give us that 9 plus y squared is equal to 4, or y squared should be equal to -5. And now you'd have to take the square root of a negative, which means you have a complex number. And thank goodness we're not doing complex calculus. Complex calculus certainly exists. It's math 421, I believe. And, by all means, you're invited to go and take that class. But we are just doing real valued calculus, right? We're sticking with the real numbers here. And so, for instance, x could never be equal to 3, right? It has this restriction on it. Z, on the other hand, does not have any restrictions. So thinking about this in terms of restrictions, right, Z can be anything that it wants to be. So long as you have basically your copy of your circle, so imagine if I did Z equals 0, that's going to be Z equals 0, that's in the XY plane, right? We haven't gone up and down at all. We're staying in this XY plane right here. So if I was to just think about Z equals 0, right? Well, we'd have a copy of our circle here in our classic XY plane. However, Z doesn't have any restrictions on it. So we could also do Z equals 1, which means that we would have a copy of our circle that's just been shifted up 1, right? So now the height, the Z value for all of these things would be 1. But otherwise, I'm going to do my best to sketch this here. Be an exact copy of the circle here, just raised up by a height of 1. Or likewise, you could do Z equals 2, or Z equals 3, or Z equals 5, or Z equals -1,000,000. And so can maybe anyone venture a guess now of what kind of shape this is going to be? A cylinder. Yes, absolutely. So this is an infinite cylinder. You have copies of the same circle of radius 2, right? Every single z value going up and every single z value going down. So for this, I'm going to go ahead and say it's an infinite, oops. We're going to say circular cylinder with radius 2 opening in the z direction. Let's play this game one more time. In fact, I'm going to go ahead and give you guys maybe 3 minutes or so to try this one on your own, right? Z equals y squared. I'd like to, sketch this in R3, describe it in words as best as possible. But I'm going to shut up for a couple minutes and let you guys attempt this one. All right, so that's a little bit of time there. Why don't we do a quick discussion about this? So I saw in chat there's a good idea. I like the sounds of this, right? A parabola with an open direction of x. And so, yeah, if you think about this, maybe first drawing it, right? Before we had x's and y's, so it really made sense to draw this in the xy plane. Right, z was missing from it, and so it made sense, right, to draw it in the xy plane since there weren't any z's. In this case, because there aren't any x's, right, you actually get a decent picture if you draw this in the yz plane, right? And notice when I'm thinking about this, right, I'm kind of thinking about the old classic y equals x squared sort of deal, right? I know that this is a parabola that opens in this positive y direction. Here, things have been kind of jumbled around a bit though, right? Our independent variable is y and our dependent variable is z, right? Z equals y squared. And so you do have to kind of rearrange things a bit awkwardly here in order to get this to kind of maybe convince yourself that this is the way it should look. And so, yes, if we have x equals 0, that is, we're just in this yz plane right here, we would have a copy of this parabola. However, x has freedom, right? There are no restrictions on x. So x could be equal to 1 out here, and in which case, again, we would still have the restriction that y squared would have to be equal to z. So it would have to live on this parabola here. And likewise, x could be equal to 2. Or x could be equal to some negative number way back here. And you can see if we kind of combine all of these things, right, we are going to get this interesting kind of parabola, like this curvy piece of paper that's kind of opening in this x direction. Something like this. So yeah, the statement though of, what is this, right? This is actually in Calc 3 speak, you would still call this a cylinder, and we'll give you a formal definition of a cylinder in 12.6. So that's why I was kind of careful to call this a circular cylinder, not just a general cylinder. So with math speak, this would be a parabolic cylinder kind of opening in the x direction. So that's what I'll write down here. Parabolic cylinder. Opening in x direction. All right, and I think I saw a hand raised here. Let me go and grab that. Adrenal, yeah, how's it going? You can go ahead and unmute yourself if you'd like.
Can you hear me?
Yes, sure can.
Sorry, it's my bad. My microphone is a little crap. So the graph we graphed in here, like previously what it did in example 1.6b,
Yes.
we graphed y equals 1. So y can be anywhere in that XZ plane, but the equation will be just y equals 1, right?
Oh, sorry. I was looking at this one. I didn't. So yeah, looking at this one here. So yeah, one way that you could think about this is if you graphed it in that, just like you said, the XY plane, you would have this line right here, y equals 1, and the XY plane looks like this. Y equals 1, the XY plane, that's exactly the picture here. But now imagine you don't have any restrictions on Z, right? So we graphed y equals 1 in the XY plane, but Z could be equal to 1, Z could be equal to 2, Z could be equal to -30 if we wanted, right? So you get copies of this. Basically, you can drag this line more or less up and down as much as you'd like.
Gotcha. So the like y equals 1, it's gonna be the equation for the line itself, right?
So y equals 1 is the equation for the plane itself.
Okay, gotcha.
Because
Right.
again, you have to, it's within the context of being in space rather than in a plane already.
Gotcha. All right, thank you.
Yeah, of course. All right. Let's see. I have a question also. Why is z equals y squared considered a cylinder? So yeah, basically, this is getting a little bit ahead of us because again, we do get into this in more detail in 12.6. But to some extent, I could just say that this is the convention. This is the name that we've given these things. Kind of anytime that you have basically a copy of a two-dimensional structure that you've copied and pasted forever in some straight line to generate your surface, this is what we call a cylinder. So we'll get into more details about this in 12.6. But I agree, it's a bit strange, right? Because that's not the geometric definition for a cylinder. All right. Going on, we have one more section to get through and only 10 minutes, sadly, to do so. So I'll speed a little bit through. This is a little bit more algebraic heavy, which is fine. So maybe we don't need as much time. So we're going to upgrade, right? And we're going to talk a little bit about spheres. We're going to talk about distances, all that sort of stuff, right? So first I need to give you a distance equation. And remember that the equation for a circle, and likewise going to be the equation of a three-dimensional circle, aka a sphere, is going to be based on the distance equation. So the distance between 2 points, P1 and P2, that have coordinates x1, y1, z1, x2, y2, z2, is given by, and you can imagine back from your algebra days, right, when you just had the two-dimensional coordinate system, right, x's and y's, it used to be something like this: x2 minus x1 quantity squared plus y2 minus y1 quantity squared, right? Add them together, throw them under a square root, and that was your two-dimensional distance. As these words up here say, we can get a three-dimensional distance equation by just sprinkling in some z's, right? And so as you would probably guess, right, the way to get this into 3 dimensions is that we're also going to take into consideration, right, these z coordinates, right? So we're going to do z2 minus z1 quantity squared, add that on to the mix, throw it under the square root with the rest of them, and this right here will indeed be correct for a 3-dimensional distance equation. So maybe let's quickly use this to come up with the distance between 2 points here. So square root of, and I'm going to do these ones as my x1. Oops. You know what? Actually, let's have a little bit of fun here, right? You guys do this. You guys do x1, y1, z1, right? That'll be the x1, y1, z1 for you guys. But actually, let me switch it around. Let's suppose that I'm going to do this instead. And I'm going to make these my x2, y2, z2 points here. And let's just verify, right, that the order doesn't matter. If I say to calculate the distance between 1, 2, 3 and 3, -1, 0, versus if I say calculate the distance between 3, -1, 0 and 1, 2, 3, right, the order in which I say those things shouldn't matter. But let's go ahead and verify, given this formula right here, that they indeed do not. Yeah, and Adrenal has the right idea. With the square, it's very forgiving. Exactly. So I'm going to have 1 minus 3 quantity squared. Again, yours will be the other way. I'm going to have 2 minus a -1. And I'm going to have 3 minus 0. All quantity squared. So this is going to be what? -2 quantity squared will be 4. 3 squared will be 9. Oops, I forgot a little 2 there. And then another 3 squared is going to be another 9. So it's going to be 9 and 9 is 18. Plus 4 is 22. So yeah, I agree. Root 22 will be the distance between these 2 points. And again, if you had them in the opposite order, you'd be squaring a few more negatives, right? But again, you would get the same result. Because whether you square 3 or -3, they both come out to be 9. All right, now let's get into spheres. Three-dimensional distance, we can define the set of points equidistant from a center point. And when we did this in 2 dimensions, right, the set of points that's equidistant from some center point, right, maybe they're all distance 2 away, sort of deal, gave us a circle. If you play the same game in 3 dimensions, though, and you're allowed to come out of the paper, right, you're going to get a sphere. So if you want the distance to be the same, right, for our sphere, and we have some center, which maybe is H, K, and L, I suppose, and a radius of R. Well, remember the distance, the circle equation was something like x minus h quantity squared, y minus k quantity squared was equal to r squared. That's what the general equation for a circle is in 2 dimensions. And of course, we can just sprinkle on some z's and we'll get the equation for a sphere in 3 dimensions. Z minus the z center. So z minus L quantity squared, I just add that on, and that gives us the equation of the sphere in 3D. So here's a relatively simple problem to try. In the interest of time, why don't I go ahead and we just do this one together. And then we got 2 more problems on the next page, but this is kind of based off of one of these WebWork problems here. Very quick problem though. We want a sphere of radius 2 centered at some specific point. So I'm going to go ahead and do x minus 1 quantity squared, y minus a -2 quantity squared. Of course, many of you probably just said, well, let's not do minus -2. Let's just simplify this and do +2. That's good too. And then finally, we have z minus 3 quantity squared is equal to the radius squared. 2 squared will be 4. So if I tell you a center and I tell you a radius, right, it's pretty straightforward in order to come up with an equation. However, going in the other direction is more difficult. And so the last 2 problems that I have here is an easier one and then a full strength one of how to go in this opposite direction. And so describe the surface x squared plus y squared plus z squared in words as best as possible. We've played this game a couple times now. Of course, we can see on the format, right, we're not going to try to solve this z equals or y equals or anything like this, right? We notice that this is the standard form for a sphere. And so in this case, if we wanted to be very particular, right, we could write x minus 0 squared, right, instead of x squared. And you could write y minus 0 quantity squared. And you could write z minus 0 quantity squared. And you could notice that 1 is, of course, the same thing as 1 squared. And so this right here will be a sphere centered at 0, 0, 0. That's my h, my k, my l. And it has a radius, right, equal to 1. So, and radius. All right. So this is the easy version. Good first problem to do on the matter, right? But the more complicated version looks like this right here. And you may remember this from your favorite algebra class. Describe this surface in words as best as possible. And notice that we have like not just x squared, but we also have minus 2x. We have some like z's here, right? It doesn't maybe look so straightforward, is right. It's even hard to say just by looking at this that it's necessarily a sphere. So we need to spend some time rewriting this into a nice format to convince ourselves that it is a sphere, first of all, right? We really haven't talked about any other surfaces in great detail. I mean, this is an entire section right here about spheres. So yes, it's going to be a sphere, right? But we still need to convince ourselves of this. I mean, imagine if it was a quiz or an exam and we've learned about other things, right? But there's needed to do some rewriting. And so, yeah, I see in chat here, someone just mentioned that, yeah, the technique that we need to use in order to get it in this good format is completing the square. So this is the old algebra technique that we need to use in order to solve this problem. So let me just remind everyone over here. So in order to do this, we need to complete the square. Oops, the square. So let's go ahead and spend some time reviewing completing the square. So for completing the square, you spend a lot of time with this value that's next to the linear component, right? So you have your quadratic piece. That's all good and everything, right? This piece right here is typically called the b value. The first time that you did this, right, is when you had probably a quadratic where you had something like maybe y equals x squared minus 2x plus 5, and you may want to complete the square for this in order to solve it and find its zeros and things, right? So again, that kind of makes sense why you would call this thing the b value, because it used to be a, b, c sort of deal. So that's the b value. And in order to get the piece that you want to add on, you do b divided by 2 and you square it. And remember, it took a while to kind of convince ourselves that this is the right thing to actually do, right? That this is this good quantity to add on. But now that we know this, right, we can apply it fairly quickly. So I'm going to go ahead, x squared minus 2x. I'm going to take my b value of -2. Oops, -2. I'm going to divide it by 2, and I'm going to square it. So this is going to be -1 squared. -1 squared is going to be 1. So I would like to add a 1 here. Notice that for y's, well, y is already a completed square, right? There is no linear component. And so y is perfectly fine as is. However, for z's, right, z has a linear component, right? We have this 4z, we have this b value there. So in this case, the b value for the z's is going to be 4. So we're going to go ahead and we're take our b value, divide it by 2, square it. So when you take 4 divided by 2, you get 2, you square it, you get 4. So I'd like to add 4 here. Now, when I do this, this is now a completed square, which means if you try to factor this, right, you're going to get x minus 1 times x minus 1. So that is, it's just x minus 1 times itself, or quantity squared. So right, when you factor it, you notice that you actually have a perfect square. So the nice way to write this is x minus 1 squared, right? It's x minus 1 times itself. Here you have y squared. When you try to factor this one, you're going to get z plus 2 times z plus 2. So this is, again, just z plus 2 quantity squared, right? So you have these nice completed squares. So the center is at 1, 0, -2, and the radius I have here is 2, and I've made a mistake. Can someone tell me what my mistake is? Yeah, exactly. You guys got it. I added things, but only to one side of my equation, right? I added a 1 here and I added a 4 here. So in the process of completing the square, I've added things to the left-hand side of my equation. Of course, whenever you do that, you also have to add things onto the right-hand side of the equations. Otherwise, they're no longer equal. So this right here should really be 9. And in which case the radius is 3. The last thing that I want to draw your attention to, I know we're a couple minutes over and I'll let you go here, but do take care, right? That I see many people, you know, especially back in the algebra days, but even if you're going too fast here in calculus 3, right, they may say that the center here should actually be at -1. And for instance, right here should be at 2 rather than -2. But notice in our equation, right, those negatives are built in, right? So we have x minus h, right? So the center is at H. So when you see something like X minus 2, right, that minus is already taken into consideration there, right? H is 2, and so the center is at 2, right? So that's just one last thing to be careful about. Okay, I'm going to stick around for some time after class, typically, to take any one-on-one questions. The first order of business, and I'm going to go through all the Q&A that I've been kind of ignoring here as I'm trying to get through this. So let me stop the recording, and I'll go through the Q&A questions.